All right, everybody, this is just a short video to derive the lens equation, which, as you might remember from class, is given by 1 over f, 1 over the focal length, equals 1 over the object distance plus 1 over the image distance for any converging lens. For any lens, it turns out we can use this equation, which we'll see how it's widely applicable later on this week. Okay, so I have two of the same diagram right here because it'll be the easiest way to show this, showing an object, which is a pencil, labeled by object distance, and then forming an image of a pencil that in this case is slightly larger and inverted on the other side. The focal point and focal length of the lens is clearly marked off in both cases, and the two diagrams are identical. I'm going to start with the diagram on the left and ask you to focus on two similar triangles. And I want you to convince yourself that they're similar and just visualize them. Because what's cool about this derivation is it's really purely geometric, which is what's fun in general about the ray model, is that there's a lot of geometry and everything really comes down to angles and geometry mixed up with a tiny bit of physics. Okay, here's two triangles, the one formed by DO and DI on the bottom. You can see that the pencil and in each case is smaller and larger, so I'm going to label the height of the pencil. This is height of the object, and this is height of the image. Convince yourself that these two angles are the same, these are both right angles, and therefore this third angle is also the same, making these two triangles similar. And you know when you have similar triangles, you can write ratios between the sides. So let's do that. We know that HI is to HO as DI is to DO. In other words, this side should be to this side as this side, which remember is this, should be to this side, which is that. All right, that's our first equation. That's all we can really get out of those two similar triangles, but it's really important. And what this tells us loosely is that the bigger the DI, the further away an object, also the bigger the image is going to be. And so the heights and the distances go in the same ratio. Now let's take another look at a different triangle. And these are a little harder to see. It's these ones in here. This little similar triangle and this little similar triangle. Now let's do some labeling here to see how this is going to be potentially useful to us. So we still have the height of the object, and notice because this ray is parallel, that means that this side of that triangle is still HO. And for that first little triangle, we know the base is actually the focal length, the distance to the focal point. Here we still have the image height, same as before. But now, what is this? And you'll notice that DI is the distance from the lens to the image. F goes to the focal point. You can convince yourself that this little leg of the triangle is then given by DI minus F. If I have the full DI and I have F, then DI minus F is that little bit. And again, I can write similar triangles. I can write HI is to HO as DI minus F is to F. And now I have two equations, and you'll notice the lens equation has no heights in it. So let's substitute in for HI over HO, DI over DO. So combining these two equations, I get DI over DO instead of HI over HO equals DI minus F over F. And then I'm not going to do all the algebra out. A little algebra will convince you that, this can be manipulated into the lens equation, which is 1 over F equals 1 over DO plus 1 over DI. And if you want to practice up your algebra skills, you can go ahead and show from this, you can arrive at that. And that's the lens equation. So how do you use it? Well, you'd be given, presumably, the focal length of the lens. Let's say it's 10 centimeters. Someone tells you that. And you always kind of know usually where you're putting the object. So let's say we put the object at 30 centimeters. Excuse me, I got something in my throat. So we would do 1 over F, which is 1 over 10, equals 1 over DO, which is 1 over 30, plus 1 over DI. And then 1 over 10 we can write as 3 over 30 And then 3/30 minus 1/30 is 2 over 30 is 1 over di. Therefore, di is 30 over 2, which is 15 centimeters. And that's how you use the lens equation. And we'll see there's some cool corollaries of this, like if you plug in a value for DO that's less than the focal point, so the object is really close to the lens, you'll find that this pops out a negative value of the DI, and in the other video you could see what all of this means. All right, there you go. See you later.